Acids and bases get talked about a lot in science, and it's important to recognize that there are a lot of different definitions of acids and bases, and in general, they just represent a model for categorizing compounds based on behavior types. And you can kind of consider pretty much anything to be an acid or a base, depending on which model you're using. Since this video is just giving you an introduction to acids and bases, we'll use one of the more common definitions, which is that acids are things that ionize in water to make H plus ions, and bases are things that produce OH minus ions in water. You may also hear acids referred to as proton donors. This is because the hydrogen atom with one electron removed contains only a proton, so the H plus ion is effectively just a proton. So a proton donor would be something that provides H plus ions. So acids can be split into two broad categories. They can be strong acids or weak acids. And these strong and weak acids follow the same kind of rules as electrolytes. Things that split up 100% into their ions when they dissolve in water are referred to as strong acids. Things where only some of the compounds will split up into ions at any one time are weak acids. There are 7 main strong acids, and it's really just worth memorizing these things so you don't have to look them up later. And in general, strong acids are going to be written with the acidic hydrogen on the left-hand side of the formula. And again, because these are strong acids, they'll dissociate 100% when you dissolve them in water. So in general, they'll follow this kind of format. The molecular acid splits up into H plus and some anion. You might notice that sulfuric acid, the bottom one on this list, contains 2 hydrogens on the left-hand side. And this is because some acids can actually provide more than one acidic hydrogen. So if you dissolve H2SO4 in water, you won't just get 1 hydrogen ion, you can actually get 2. These are called polyprotic acids. And it's really hard to identify if any given molecule is going to be a polyprotic acid just from the formula. Certain things have lots of hydrogens in their formula, and they won't all be acidic. Later on, when we learn how to identify structural components of acids, it'll be a little bit easier. But for now, recognize that sulfuric acid is polyprotic and provides more than one acidic hydrogen. And if I need you to know that any other acid is polyprotic, I'll just tell you outright. So sulfuric acid, it's worth recognizing a couple of things. The first is that it has 2 dissociations, unlike all of the other strong acids. The first dissociation is a strong acid dissociation. The molecule splits up into H plus and an anion. The second dissociation is a little bit more interesting. The second dissociation is not strong. The HSO4 minus ion can dissociate, it can lose its extra hydrogen, but this dissociation is no longer strong. So HSO4 minus is actually a weak acid. So polyprotic acids have multiple dissociations, and the first one is always strongest, and then every subsequent dissociation gets weaker and weaker, and fewer of those compounds are likely to split up into the ions. And that can lead us into our discussion of weak acids. So weak acids are compounds that when they dissolve, some percentage of the sample will split up into ions, but the vast majority of the compounds are going to remain molecular. They're going to remain associated. And over time, some will split into ions, some will reform into molecules, and they'll have a dynamic equilibrium going. And these molecules are often, but definitely not always, written with the acidic hydrogen on the right-hand side of the formula. And a couple of the more common examples that you'll come across are things like acetic acid or the ammonium ion. So you can see in the case of weak acids that we still have the compounds dissociating to form the hydrogen ion and some other component. But in this case, our reaction arrows are the equilibrium arrow, implying that only some percentage splits up into ions. And in the case of the ammonium ion, it's worth noting that when the ammonium ion loses its proton, so it dissociates, it produces H plus and NH3, the ammonia molecule. And the hydrogens in ammonia are not acidic at all. Ammonia is actually a fairly strong base. So this is again to point out that knowing the structure of molecules and how that influences the acidity or basicity of that molecule is something that we'll talk about later in the course. And in general, there are too many weak acids to memorize. So in general, the rule is if it's not one of the strong acids, and I tell you it's an acid, then it must be a weak acid. So bases, unlike acids, produce OH minus in water. They may or may not actually contain OH minus as part of the structure of the compound, but when they're put into water, OH minus will form. And that might sound a little bit odd, but it'll become a little bit more understandable when we talk about the difference between strong and weak bases. Strong bases, again following the rules for electrolytes, they split up 100% into their ions. You dissolve this base and every one of those compounds will dissociate. And just like with the acids, it's easier to memorize the strong bases than it is to memorize the weak ones. The strong bases effectively just consist of the soluble metal hydroxides. And this is because if you can get a metal hydroxide to dissolve, metal hydroxides are ionic. If you can get an ionic thing to dissolve, it will dissociate 100%. So the soluble metal hydroxides are the group 1 hydroxides and the heavier of the group 2 hydroxides. And the dissociation of these metal hydroxides looks very similar to the dissociation of a strong acid. Weak bases are a little bit different than the weak acids. You can almost think of them as having two different categories. Weak bases containing hydroxides and the other weak bases. The weak bases with hydroxides are basically any metal hydroxide that is not a strong one. So anything that doesn't belong to the group 1 or heavy group 2s. So these include things like magnesium or aluminum hydroxide. And because these don't belong to the group 1 metal hydroxides or the heavy group 2 hydroxides, they're not very soluble. So they don't dissolve to any great extent. So they can't produce significant amounts of hydroxide relative to the amount of starting material. And again, you can see an equilibrium arrow in this situation, implying that they don't dissociate to any great extent. So the weak bases without hydroxides behave a little bit differently. They still produce OH-, but they do it indirectly rather than directly. And the easiest way to explain that is to use an example. So the most common weak base that you'll encounter is likely to be ammonia, and ammonia obviously contains no OH- groups. So it can produce OH- in water though, and it does it by actually reacting with the water itself. So you take ammonia and you dissolve it in water, and as part of that dissolution, the water and the ammonia will interact and they will create products. In this case, the ammonia has actually taken one of the water's hydrogens to make NH4+, and the leftover bit of the water is an OH- group. And that's how ammonia can actually produce OH- in solution. And the other weak bases that don't have hydroxides are going to behave in a very similar fashion. And again, just like with the weak acids, there's no point in trying to memorize all the weak bases. If I tell you something's a base, you can check it against the strong bases. If it's not one of those, it must be a weak base.